Open up share slideshow. Can you try to say something? Hello? 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 Yeah, hello. All right. Oh, wow. That boom. Okay. Hello. Hi, everyone. Welcome back to CIS 5480, 4480. I'm Travis. I'm back to spring break. Hopefully, you all are doing all right. Feeling good? Feeling refreshed? Excited to do more operating systems? Yeah. That's what I like to hear. All the enthusiasm. Okay. All right. I'm not going to fuck with you too much more. All right. Here is some logistics things. So this lecture is not going to be given by me or Joel. We'll both be here still. But we're going to have the TAs give this lecture because this lecture is all about PennOS. PennOS is the big project that takes up the second half of the semester. This is like almost entirely, other than like the final exam and maybe one or two small other things. This is most of what your time is going to be spent on in this class for the rest of the course. And if you've seen the spec already, you'll notice the table of contents itself is like takes up a whole page. It's or close to it. There's a lot of stuff here, right? So we find it useful to dedicate a whole lecture just towards going over a lot of things about PennOS, demoing some of it, and trying to make, I don't know, your lives as easier as possible. Hopefully you've taken a look at the spec already. If not, hopefully soon. A little bit of logistics related to that. So mid-semester survey, that was supposed to be posted already. It's not out yet, but it'll be posted very shortly on Canvas. It is going to be due end of day, so a week from now. Credit, no credit, it's anonymous. I cannot tell, I can see the answers, but I can't see who submitted them. So that means it's anonymous unless exactly one of you fills out the survey. Then I'll be able to tell what your answers are. But assuming there's more than one submission, it is anonymous. Please be honest in it. We use the feedback as best as we can to change the course. We do change the course every semester to try to make it better to varying degrees of success. But we do try to listen to feedback. We might not be able to implement the feedback mid-semester, but we still value it. PennOS groups, that it was posted before spring break. You need to join the group on Canvas to secure your group in PennOS. If you have figured out 3 of the 4 of your group and can't find the 4th, still join you 3 together in one group on Canvas, right? Just so I know that you 3 want to stick together. But you need to do that ASAP, like right now, if you haven't done so already. Like actually, if you haven't done it yet, go do it right now. Because after midnight tonight, we're going to randomize the groups, and we aren't going to like a week after it's due refix the groups like we did for Penn Shell for some of y'all folks. You need to be in the groups, all right? So do that ASAP, random assignments end of day. So you'll be posted probably in the early tomorrow morning, and you'll also be posted which TAs did which parts of PennOS and which groups are assigned to which TAs. Because each group will be assigned 2 TAs, 1 or 2 TAs, and that will be your go-to person when you have questions about PennOS. And they're the people who you're going to go to when you demo PennOS for a grade. do in the week of 324 to 328, so not this week, but next week, this is going to be similar to what's in the spec. It's going to be you need to show up to meet with your TAs, but you need to do more than just meet with them. It's not just meeting with them. You need to demonstrate that you've thought some about PenOS, how the work is going to get done, how it's going to be split up, and some thoughts on the core structure of how things work. Like you're going to need to be able to explain the SP-Thread sketch demo code, for example, the scheduler demonstration code. You're going to need to be able to explain what you think you'll need to put in your process control block structures. Milestone 1 will be 2 weeks after that, and this is where you're going to need to demonstrate core functionality for the file system and the kernel, and then sometime later there'll be the final submission. After that, you're going to, once you've submitted your code, you will need to meet with your TA to demo it. Because unlike the shell and shredder, there is some autograder for the file system, but for most of it, there's no autograder. So we do have a demo plan where given these inputs, we expect roughly these outputs, but you're going to have to demonstrate these things for us. And you're going to have to explain your code to us and show some of your code and your documentation for us. I think that's it, right? I'm going to let the TAs do the rest of it. Stay tuned. And yeah. Thank you to the TAs for doing this.
Hi guys, I'm Akash. If you guys don't know, I'll be doing the first half of this presentation. So the grading for PenOS is as follows. We have 5% for documentation, 45% for the kernel and scheduler, 35% for the file system, and 15% for the shell. This is like different from the shell you guys already created. It's because you have to run your own functions that you create. For the documentation, we have two different requirements. We have a companion document and a README. And the companion document is essentially an API spec. It's just like a description of all the functions that you write. It's similar to like an API spec that you would find online if you just look it up. The API spec essentially describes how the OS is built and how to use it. And one tool we recommend using to create your API spec is Doxygen. If you look it up, there's like a specific way to format your headers, your header guards. And if you do it this way, and you can auto-generate your API spec with Doxygen. We highly recommend using this because your API spec can probably be over like 30 pages. Mine was like 35 pages. And you probably don't want to write this by hand. So figure out how to use Doxygen. The other thing we require as documentation is README. And this is like a general implementation kind of thing. We don't want you to write every function and every purpose in the README. That's for the companion document. The README is for general design choices, implementation details, why you chose to do what you did, and how you organized your files and stuff like that. So today, I'll be going over the PenOS overview and the PenFat file system. Then I'll hand it off to August to do the scheduling and process lifecycle and SP-Threads part of the lecture. And then Connor will do the PenOS shell. And then finally, we'll do a demo at the end. But please ask questions, guys, as I go through. This lecture is really dense. So if you don't ask your question, you might forget it later. So first, I'll go over generally what PenOS is. So far, we've done PenShredder, which is essentially like a mini shell with signal handling. And then we moved on to PenShell, which handles a couple more different features like, sorry. Oh, sorry. So we moved on to PenShell, which has a little more features like redirection and pipelines, process groups and terminal control and job control. And these are important because we're building on top of these features in PenOS. We still have signal handling. We still have redirections. We don't require pipelines for regular credit, but we use process groups and job control. We have background foreground processes still. All of the stuff you learned is important to apply in PenOS. The difference between PenOS and these projects before is that in these projects before, you use stuff like exec v, execvp. And what those functions do is they take an executable file, like for example, cat. Cat has an executable file, and it runs those files automatically. The difference in PenOS is you're going to create these functions from scratch. Like you're going to create cat from scratch. You're going to create sleep from scratch. So this is essentially how PenOS looks, like a very simple diagram. We have like our main functionality in the middle here with our IO and scheduler. The IO interacts with your file system. These are calls like cat, calls like copy, stuff like remove, stuff that directly interacts with your files. and it will interact with your custom file system. We also have the other main part, which is the scheduler. And this directly interacts with the jobs. It manipulates the job states. So like if the job is a zombie, the job is stopped, stuff like that. And it also directly impacts the job queues to determine which job goes in the foreground, stuff like that. So like the user will input their commands, the scheduler will run the command and then take care of all the states and stuff. And then the user will input their file system commands like cat, and then the PenOS should take care of all of the underlying stuff that happens, like the reads, the writes, stuff like that. So we promised you guys that you would create a OS at the end of the semester, but we kind of lied to you a little bit. We're not actually creating a real operating system. It's kind of like a mock fake operating system. To create a real operating system, it requires a lot more than what we're doing here. There's a lot more software, underlying software to connect it to the physical hardware. And it's a little outside the scope of this class. So instead, what we're having you do is you're creating PenOS as a process within your Linux kernel. So there can be other processes going on like Bash or X11 or maybe even PenShredder. But PenOS and all of the abstractions within PenOS run as a single process within your kernel. This is similar to how it is for PenShell or PenShredder. You just run the PenShell and PenShredder executable, and then you're able to run the commands. Is there any questions about the general structure of what PenOS looks like? Yeah, so it's just a single process, and PenOS will take care of everything within that single process. You don't really have to worry about this that much. It's just to make your life simpler. All this stuff here will be taken care of by your Linux kernel. Everything that you have to take care of is within that single process. So an important part of PenOS is the abstractions, these user system and kernel abstractions. The reason that these are important is because say you have like a shell, right? And you run specific commands like cat, echo, stuff like that. These commands are not directly impacting your file system. So we're not having the user directly write and read bytes to the file system. Similarly, when we create processes like sleep, we're not actually directly letting the user create processes. They're kind of indirectly doing this by creating their sleep, right? So like when they create a sleep process, the underlying kernel will create a process and then run the process automatically. We don't want the user to automatically be able to do these underlying features. We want this to be abstracted away. So the reason why we have these different abstractions in PenOS is so we can have these different distinctions. So userland, in this case, means the functions that the user can actually run. Think of this like the terminal commands, like echo, sleep, remove, copy, cat, whatever. What actually happens under the hood is what we call kernel land. And these are like system level functions. These are like stuff like read and write, or something like create process, or create process block for a process, stuff like that. This is what happens indirectly when you run a user level command. To kind of connect these two lands together, we have something called a system land, which is the APIs that the user land calls, the user functions call, to invoke some kernel function. The reason we have the system land, the reason that it even exists, is because we, in our specification, we don't allow user level functions to call kernel level functions directly. Instead, they must call system level functions, which inherently call kernel level functions. The reason this exists, additionally, will become more clear as you start coding the project. System level functions often are associated with processes, individual processes. But yeah. So how this looks in our diagram from before with user and kernel land is, if you look on the left and right here, the red parts, this is the user land. And in the center with this gray, that's the kernel land. So the user directly interacts with the user land. So in terms of the left here, with the PenFat file system, this is stuff like cat, where we directly impact the file system from a user standpoint. And then stuff on the left here, where we run commands and jobs through the shell, like sleep. These user level processes will indirectly invoke kernel level processes. So in terms of cat, this will read and write to file system, right? And in terms of the scheduler, running sleep will create a process and put it into the job queue. These are like the underlying under the hood stuff that happens in the operating system that we don't have to care about as a user. Is there any question about like the distinction between user and kernel land, system land, whatever? feel free to ask later about this too. So now I'll move on to the file system portion of this lecture. So first, a quick refresher on about what is a file system. I know you guys just took your midterm, so I won't be too long on this, but essentially a file system is a way for your operating system to organize different pieces of data, persistent data. And our unit here is a file. And essentially a file is just a sequence of data containing blocks. And this data doesn't necessarily have to be contiguous, as we've seen. In FAT, these blocks are actually not contiguous. So quick refresher on what FAT is. FAT is essentially a table that allows you to traverse files quickly, allows you to access different blocks of different files quickly. And FAT is just one example of a file system. Mac, Windows, Linux, they all use different versions of file systems, but we're using FAT here for simplicity. We could use inodes, but it's a little more complicated, and we just wanted to keep the file system a little simpler for you guys. So as a quick refresher, here's a FAT example. Say I had like a file that started at block 11, and I wanted to traverse and read through this file. I would look at block 11 on the left side, see its link, it's 14. I would go to block 14 because that's the second block of this file, see its link, it's 15. Then I would go to 15, that's the last block of the file, as indicated by the -1. Is there any questions about FAT? I know you guys probably know this, but. So we have this like abstract notion of this table where it kind of links blocks together, right? But how does this physically map to how we implement this in PennOS? So actually, PennOS, the file system, all it is just a single binary file and just a binary file of bytes. And you basically directly manipulate these bytes to change your file system. So this is kind of how it's laid out. We have the FAT, the physical table FAT at the start of your binary file. And then the rest of the blocks are the data containing blocks that we manipulate to change and change files around, change directories around. So how do we go from this table, this abstract table, to this binary file and these bytes? We have this function called mmap. Essentially what mmap does is, given a binary file, it will return an array. And in this array, if you go to like index I and manipulate index I in that array, it will directly manipulate the ith byte of this binary file. And definitely use this function. It makes it a lot easier to think about and reason about using this binary file. You definitely don't want to manipulate bytes in the binary file directly. This makes it a lot easier. Is there any question about how PennFat is actually implemented and how it's laid out? Yeah. It's a binary file. It just has bytes. So like the blocks are there's something that you define. It's not something that's like there inherently. It's something that when you calculate what's in block 3, you have to do the math yourself to get there, like given the block size. I'll go more into the math later, but that's just a little summary. Yeah. Yeah, just a binary file. Yeah. So I've talked a little bit about the FAT, so now we'll talk a little bit about how files are distributed along the FAT. So before we saw that there's a bunch of these blocks down here, and these are the data containing blocks. So like our files go into these blocks. And as we know in the FAT, these blocks for a certain file don't have to be contiguous. So like say this given a file A, we have the first block is block 11, the second block is block 14, third block is block 15, but we don't fill block 15 all the way. This is how files are distributed in this scheme. And as a quick point, I don't know if you guys have seen this function lseek before, but I just wanted to make sure you guys know what it is because this is something you have to implement in PennOS. Lseek, essentially what it does is it manipulates a file's offset. So what is a file's offset? So if you open a file, the file's offset is automatically set to 0. And what the offset means is that if you start reading from the file, you'll start automatically reading from the beginning of the file. The reason lseek exists is what if I want to start reading from the middle of the file? What if I want to read from near the end of the file? We can use lseek to manipulate this offset pointer to describe where we want to start reading. So for example, in this first example, we do lseek on this file, and we want to offset it by 60. So then that's that first pointer. And if we start reading now, we'll start reading from that pointer. One small quirk about lseek is if you lseek to something after the end of the file, it will actually extend the length of that file. So if I lseek past block 15, it will have to extend the file and add another block. Is there any questions about lseek? So what if I wanted to write to this file before? Before my file looks like this, and now I want to write some data to this file. The good case, the nice case, is if we write like, for example, if we write 1 byte to this file, then we probably can just fit that byte into block 15 and we're fine, right? We don't need to allocate any more blocks. We just write the data to our file and that's it. We don't have to do anything else. Bad case is if we write too much data that we need to allocate another block. So in this case, we write block size number of bytes, and we can write some bytes to block 15, but then it overflows and we have to write more bytes to some other block. So what do? Well, first we have to find an open block, and in this case, block 22 is the open block. We have to allocate this block in order to write to it, and then write the rest of our data to this block. We need to make sure this block is free first, and how we do that is if it's indicated by a 0 in our file allocation table. But after we write the data to block 22, are we done? No, we're not done, right? We still have the file allocation table still not updated. Right now, it indicates that 15 is the last block. What we need to do now is first indicate that 22 is the next block after 15, because this is the new block, and also indicate that 22 is the last block in the file. Once we do this, we're done. This is something very important. This is when you create the write function in the file system, you will directly have to use this logic. Yeah.
For the current block, how do you know how much space there's still left within?
That's a good question. So I'll get more into this later, but in a directory entry for a file, it will contain the file size. So given that file size, you can calculate how far into the block we are. There's a lot of math here. It's very helpful to make helper functions for this kind of stuff. But these little edge cases are something very important to point out. That's good. Yeah. Yeah. Because the block size will never change. So yeah. So I'll go over this later, but in your root directory, you have directory entries. And for every file, you have one directory entry. And for that directory entry for this specific file, it will store the size of the file currently. And after you write, you also have to update that size. Something to think about. Any other questions? So that's a little bit about file allocation tables in general. And now I'll go into more specific stuff about PenFat. So essentially, all of the file allocation table in PenFat is just an array of unsigned little endian 16-bit entries or 2-byte entries. It's important here to notice that it's little endian. It's not big endian. And this will cause you a lot of headaches later on when you're trying to assign to this binary file and your numbers don't match up. Make sure you know that it's little endian. What little endian means is that the least significant byte goes first, not the most significant byte. How we create a file system in our spec is call this function mkfs. This just means make file system. And we just specify the name of the file system, the number of blocks in our file allocation table, and then the block size. And then given these two parameters, we can calculate everything about our file system, which I'll demonstrate in a second. But makefs will define this binary file, and in this binary file, we'll define a fat region and then a data region. So how do we actually calculate the sizes of our fat and data region to allocate memory in our binary file? We have to do a little bit of math here. So for the fat region, it's pretty straightforward. We have these two parameters, blocks in fat and then block size. So it's pretty straightforward to calculate the size of the fat, right? We just multiply the block size by the blocks in the fat. It's exactly what we do here. To calculate the data region, however, it's a little bit more complex. So an important distinction to make here is that for every fat entry, each fat entry corresponds to one data block. So can someone tell me, given the size of the fat region in bytes, how do we calculate the number of fat entries that we have? I'll give you guys a hint. For 16-bit entries. Yeah, it's 2 bytes, exactly. So we have to divide the size of the fat by 2 to get the number of fat entries. And then we take the number of data blocks and multiply it by the block size to determine how big our data region is. And can someone tell me why this is -1 here? Does anyone know? Why we don't use every single fat entry? We skip one? No, actually, it's we do have to have an entry for the root directory. The reason we have -1 here is because the first entry is a special entry. I think Joel went over this in the last lecture, but the first entry stores metadata about the file system. So that this entry doesn't actually store a data block. This is just metadata. And in this first entry, it's 2 bytes. So the most significant byte is the number of blocks in the fat. And the least significant byte is the size of each block. And if you notice, that corresponds exactly with the parameters that we input into the fat. So yeah. And again, each fat entry is 2 bytes. So for the least significant byte, we'll specify a number of 1 through 4, and this number will correspond to a block size of this many bytes. This will be hard-coded, Yeah. So here's some examples of the first entry of a fat. If we look at this first row, we can see that it's 0, 1, 0, 0. So then the most significant byte here would be 1. The least significant byte would be 0. So that most significant byte corresponds to the number of blocks in the fat. So that's why we have that 1 here. And this least significant byte is 0, and 0 corresponds to 256. So our block size is 256 bytes. To calculate the fat size, we multiply the blocks in the fat times the block size, which is 256. And to calculate the number of fat entries, we take the blocks or the fat size and divide it by 2, right? More interesting case maybe is this last row. This last row is the biggest file system we accommodate in PenFat. So in this case, our most significant byte is 0x20, and 0x20 is just 32 in hex. So our most significant byte is 32. Our least significant byte here is 4. And 32 corresponds to 32 blocks in the fat, and then 4 corresponds to 4096 bytes, which is our block size, right? To calculate the fat size, we multiply these two numbers together. We get that number. And then to get the number of fat entries, we just divide it by 2. Something weird here is for this edge case, fat 65,535 is undefined. Does anyone know why that could be? It's a tricky question, but. I'll give you guys a hint. So in the fat, we have a couple different special entries. Like I previously mentioned, if the entry is 0 for a specific block number, that means that that block is free. If the entry is 0xFFFF, that means that this block is the last block in its file. And finally, if it's like anything else, it's the next block of that previous block. So given information here, does anyone know why it could fat 65,535 could possibly be undefined? Yeah, exactly. So it wouldn't make sense to have an entry here because 65,535 is equivalent to 0xFFFF, and that's reserved for the last block. And something interesting about here, this largest example, the reason why this is actually the largest thing we can allocate in the file allocation table is because this is the largest number we can store in a 2-byte entry. If we accommodated something bigger than this, then we would need bigger than 2 byte entries for our fat. So here's an example of what a file allocation table might look like. In index 0, this is our metadata. This stores information about the file allocation table. And it's 0x2004, which is the same thing we just saw. So 32 blocks in the fat and then 4096 byte block size. This first entry in index 1, that's our root directory. 1 in the fat always holds the first block of our root directory. So in this case, there's only 1 block in our root directory, so it ends there. Then we have a couple files here. And at index 8, we have a free block because it's indicated by 0 here. Is there any questions about the fat in general, PenFat? So I went over the fat a little bit. I'll talk now a little bit about the data region now. So like I said before, each fat entry represents a file block in the data region. And the math is similar here. The data region size is just the block size times the number of fat entries minus 1. And the minus 1 is here because of that metadata slot in the fat. Block numbering is indexed by 1. And like I said, block 1 is always reserved for the first block of the root directory. It's so we can find the root directory quickly. The other blocks are for files. They could be additional blocks for the root directory. If the root directory gets too big, we might need to allocate more blocks for the root directory or subdirectories. This is extra credit. But most times it should just, these blocks should just be used for files when you guys use it for regular credit. So I guess now I can go over what a directory is. This might answer your question from before. A directory is essentially a file consisting metadata about other files. So it's information about the other files. And in our case, we only require the root directory. We don't require any subdirectories. And the root directory is our top level directory. All the files, if you do regular credit, should be under the root directory. So a directory entry, each directory entry is a fixed size of 64 bytes. The first 32 bytes is the name of the file. And this name must be using legal characters in POSIX. The first byte of this file name has some special values. So if the first byte of this file name is 0, that means we're at the end of the directory. If the first byte of this file is 1 or 2, that means that this file has been deleted. The distinction between 1 and 2 is a little weird. It's for extra credit. Search up symbolic links if you're interested, but I'm not going to get into that right now. Any questions about this? Continuing on, the next 4 bytes of the directory entry is the file size. So this is how we determine where the end of the file is. I think someone asked that before. After that, the next 2 bytes is the first block number. This is important. This is one of the most important parts of the directory entry. Often when you want to find a file, you'll scroll through the directory entry or the directory and look for the file name that you're trying to find. And then what you'll do is you'll look at the first block number and then reference back to your file allocation table to find the other blocks in the file. The next byte is the file type. And we have a couple different file types here. You don't have to worry about unknown. You'll never have to use this in PenOS. And 2 and 4 are mostly for extra credit because this is for subdirectories and then symbolic links. Normally, when you have files, it will be a regular file. It will just be 1. So you probably don't have to worry about this too much. The next byte is the file permission byte. It's just what permissions you have on the file. It's like you can read the table here. And the next 8 bytes is the timestamp when you created the file. So if you touch a file, you call this function time2, assign that to your directory entry, and they're good. The last 16 bytes are for extra credit. You can use them however you want if you do extra credit. So now I'll walk through an example of what like the fat and the data region look like in some simple commands. So say we just initialized a file allocation table, and it looks like this. The first thing we want to look at is that top row. That's our metadata about the fat. So that top row has 0x2002. We look at the most significant byte here. What's the most significant byte? It's 0x20. That corresponds to 32 in decimal. And as you can see, we have 32 blocks in our fat. The least significant byte here is 02. which corresponds to the size of the blocks. And 02, if we go back, it's 1024 bytes. So each block is 1024 bytes. Another thing to look at here is FAT1 always points to the first block of the root directory, like I mentioned before. And here we only have one block in the root directory. So in the FAT, its entry is 0xFF because it's the last block in that directory file. There's nothing in our directory right now, so it's just all zeros, and there's nothing in our data region right now because we didn't add anything. So that's all there is here. Is there any questions about this before I move on to creating files? So what happens when we create a file? Say we called the command touch bar. So we created a file called bar. If you look at the directory now, we created a directory entry. And here, this is our directory entry. Our file name is bar, as you can see at the top. And the next entry is the size of the file. We haven't written anything to the file yet, so the size of the file is 0. We have a bunch of other stuff that are just default values because there's nothing in the file. And finally, we have this timestamp which is the time when we created the file. But if you'll notice, there's no blocks allocated to this file yet because we haven't written anything to the file yet. It's just like the idea of a file. There's nothing in it. Once we write to the file, a lot more interesting stuff happens. So say we wrote hello to this file. What happens to our directory entry? We now have a file size of 6 bytes, as you can see by that 6 right there. This next 2 corresponds to the first block of the file. So when we write something to a file, we have to find a free block and then write to that block because there's no blocks allocated to the file yet because we just created the file. So the first free block here is block 2. We write hello to block 2 and write 2 as the first block in this file in the directory entry right there. This next line is the file type, and this is just a normal file, so it's file type 1. This next line is 6 because the permissions of the file, I'll show you, is read and write, so 6. And finally, we still have that timestamp there. One more thing, if you look at your file allocation table now, you can see in 2, there's 0xFFFF, indicating that this file is allocated, and this block is the last block in this bar file that we just created. One last thing, now that we created a directory entry here, the first byte of this first directory entry is no longer 0, indicating that this is not the end of the file, this directory entry. Now the next directory entry has this first byte of 0, indicating that is the end of the directory. Is there any questions about writing to a file? What happens when we try to remove this file? If we try to remove this file, the first thing that happens is we go in our file allocation table. If this file is multiple blocks long, we have to traverse through our file allocation table and find all the blocks that are part of this file. And what we have to do is 0 out those blocks because 0 represents an empty block, a block that's ready to be used by other files. In this case, there's only one block, so we just 0 out this FAT2, meaning other files can use this block now. The other thing we have to do is set the most significant byte, or not most significant, the first byte of this directory entry to 1, indicating that this directory entry is deleted, and some other directory entry can overwrite this. If you'll notice, hello is actually still here, but now this is pretty much garbage data because we already deallocated the block in the file allocation table. And if some other file were to use this block, it would just overwrite the hello. Is there any questions about this? Okay. So now I'll get into what the standalone PenFat is. So this is like general PenFat, what I just talked about. But standalone PenFat is what we require for milestone 1. This is basically something that is independent from the kernel. It's a way for you to run functions that just manipulate your file system that doesn't require anything else. So essentially what we require is the implementation of all the kernel level functions. These are essentially your system calls, like your writes, your reads, your lseeks, your opens, stuff like that. We require a simple shell for reading, parsing, and executing file system modification routines. And all this means is that like, this is just general terminal commands like cat, remove chmod, stuff like that. So these are like user level calls that will directly manipulate your file system. And finally, we require a system-wide global file descriptor table. This is what when you open a file, that's what it will modify. It will modify your system-wide global file descriptor table. So as part of this standalone PenFat, you have to implement kernel level functions. These kernel level functions interact directly with the file system you created. And it also interacts with the global file descriptor table, like I said. An example function is kwrite. This is very similar to write. If you'll notice, the syntax is exactly the same. We have a file descriptor, a string that we write, and the number of bytes we write. So what this does is it accesses the file descriptor associated with FD in our global file descriptor table. And then it writes that string into that file descriptor table, that number of bytes. What we're doing here is literally modifying this binary file that contains your file system to contain this string. Kwrite can get a little complicated because if we have multiple blocks over our file, we have to traverse through these blocks first and determine where we need to write. And if we write over the edge of one block, like I did in the beginning example, we have to allocate another block. So make sure to spend a little time thinking about how you do this and all the different cases that you can arise. There are a couple of standalone routines that we have to implement for the standalone PenFat. There's a couple of special commands up here. Makefs, we already talked about. It's just making a new file system. Essentially, this is just creating the binary file that contains fat and the data region. We have mount and unmount here. Essentially, what mount and unmount are is we can have multiple of these binary files that correspond to file systems, but when we're running our kernel, we only have one file system associated with the running processes. So if we run cat in our shell, we only want that to modify one specific file system. So the mounted file system is the one that we modify. So in order to use PenOS, we have to mount a file system. And unmount is just unmounting a file system so you can remount a different file system. These functions can be implemented using C system calls. Then we have our standalone routines, which are just our normal functions that users can input into their shell. These functions should only use K functions. You should never be using read or write in these functions. You should only be using KRead and KWrite, unless you interact with your host file system. And I'll give an example of this later. So just to be clear, your file system refers to that binary file that you create, that binary file that you just modify the bytes. Your host file system is your actual Docker's file system. So here's an example of a standalone routine. It's just cat. The syntax here is a little weird. This is how you'll see it in the spec. But essentially what this means is that we're catting this file. This ... means that there can be multiple files, so like multiple of the parameter before it. So we can cat multiple files. We want to take the contents of these files and output it to standard out. But we also have this optional parameter within the brackets here, which indicates instead of outputting to standard out, we output to this output file. So to implement cat, the logical flow would probably be something like this. You'd open all of the files in cat. So like if there's multiple files, you k open all of these files. And if there's an output file specified, you would also k open that file. You would have to read all of these files and then output those to your output file. So you'd need to kwrite those to your output file if the output file is specified. Is there any questions about how you would implement cat? Just make sure you notice that it's k open and k read and k write. Because if you use normal read and write, these do not work with the binary file. This k open, k read, and k write are specially designed to work with your block system, your file system, everything. If you use read and write here, you'll get a 0 in the assignment. Another example of a standalone routine is copy. And this is a standalone routine that can potentially interact with the host file system, as indicated by the H flag here. Essentially what copy does is it takes that source file specified in source and copies it to the destination. If there's no H flag specified, the source file exists on your file system. If the H file is specified, it exists on the host operating system. So the logical flow of something like copy would be like this. If the H flag is specified, you would read, not k read, from your source file, because the source file is hosted on your host operating system, not your operating system, and then you would k-write that file to the destination on your operating system. The other case, if this source file exists on your file system, is you would k-read instead this source file and then k-write this source file to the destination. Is there any question about like how the logical flow of these routines would work? Yeah. So sorry, I didn't make that clear. For this example, because we want to interact with the host file system, because we specify the H flag, it's okay to use read, but only in this case. Some of the standalone routines will have this H flag, and only then is it allowed to use C system calls. But otherwise, you should always be using your K calls, K read, K write.
Still to read a binary file on our CanOS, still to read the files from our CanOS file, you still need the.
Yeah. Yeah, I didn't make that clear, sorry. So within K read and K write, you can call read. But within these like standalone routines, which are like user level functions, you can only use your kernel level functions. You need it.
You Zoom? Yeah, once. All right. We're now switching it over to August. We're going to talk about the Catalyst kernel. Give us a second while we set that up.
This part I can maybe like
set up the demo on someone else's laptop.
Yeah. Or if worst case, you can like record it or something.
Yeah.
Okay.
Because my demo is for the scheduler, not for the shell.
Okay. All right. All right, we're back. Hello. So, a little bit of technical difficulties. It is okay now. So because of technical difficulties, we might not be able to demo part of the things we were planning to demo. We'll either come back to it at the end of lecture if we can find a workaround, or post a recording. But for now, I'll hand it over to August. He's going to talk about the kernel part of Panelist.
Okay, so I'm gonna go over the kernel part. So to start off, let's talk about the scheduling algorithm. Basically, it's a good old round robin scheduling algorithm with priority queues. So here, as you can see, we have 3 queues, each associated with a different priority level. Q0 has priority level 0, Q1 has priority level 1, Q2 has priority level 2, and Q0 is supposed to be scheduled 1.5 times more frequently than Q1. So the higher priority level will be scheduled more frequently. So let me give you a scenario. If I have a process in Q0, which is in this case shell, and I have 2 other processes. So let's call this process 1, and then we have process 2, process 3 in Q1. And I have 100 time quantum. How many time quanta should each process run? Process 1, and then process 2, 3. Anyone? How many time quanta for shell? The single process in Q0. What do you think? So basically, all the processes in Q0 should be run more frequently, 1.5 more frequently than processes in Q1. So we have 1 process in Q0, 2 processes in Q1, and they're sharing 100 time quanta. So in that case, is 1.5 to 1, so 3 to 2. Basically, all the processes in Q0 should run 3 out of 5 of the time quanta the total time quanta. So basically 60. 2 processes in Q1 will share the rest, which is 40 time quanta. So each process will run 20. Does that make sense? Yeah, so basically processes in Q0 should run 1.5 more frequently than processes in Q1. So in terms of the number of quanta used by the processes in each queue, it will be 1.5 to 1, so 3 to 2. So basically Q0 will take up 3 out of 5 of all the time quanta. Does that make sense? It's basically 3 to 2, right? And then 5 is like the total. Does that make sense? Yeah. Oh well, in terms of like shares of time quanta. So Q0 will take up 3 shares, and then Q1 will take up 2 shares. And then in total there's 5 shares because it's 3 to 2 in terms of the frequency. Good? Okay. All clear? And I think Connor will talk about this later, but shell will always be in Q0. So it will always be in the highest priority queue. In terms of process lifecycle, this is pretty similar to what you learned in lecture. So basically, you type in a command in shell, and you create this process. For example, if you type sleep in the shell, you have quote unquote process that's actually running as a thread. You call spawn, which is basically how you start a process. And in here, you would want to basically init a lot of things. So like your process control block, which we'll talk about later. So after that is spawn, basically it's going to go into running state. It could be blocked, stopped, and it could be killed as well. So here you have your kill function. And bear in mind, these you're supposed to implement yourself. You're not supposed to use the kill system call, right? So because again, we're dealing with threads instead of actual processes. So all the system calls that you used before don't apply here. So you still have your good old system signal handling, Control Z, you stop a process, and you have Control C to kill a quote unquote process. So you have to keep track of all the states. In terms of termination, yeah. So a process can simply exit, or it could be signaled, and it will go into either zombie or orphan state. So it will first become a zombie if it's not reaped. It will stay in the zombie queue until reaped by the parent. And the parent will call WayPID, and the child will basically be reaped and stop being a zombie. In the case of a parent dying, you would basically have an orphan process. And the way we recommend dealing with orphan processes is basically to have an init process. So init process sits on top of shell. Basically, once the parent of a process dies, becomes an orphan, and it's supposed to go under the init process. So as you can imagine, you have init at the top, and then init will basically start the shell process, and the shell can basically create can spawn other processes. And when these processes die, basically, they're basically the children will basically fall under the init process, which is the sort of the grandfather process. That makes sense. Any questions? Yeah. Well, they're all running as threads. Yeah, init is there to basically help you take over the orphans. Because if the parent dies, who's going to take over the orphans, right? In previous iterations of the class, we didn't have this, but in this iteration, we believe it's more beneficial for you to have an init process to basically deal with the orphans. Here you have your process control block. In here, you need information for each process. These are just some examples. We would like you to think about what else you want to put in there. Okay, so we've been throwing around threads as like a term for a while. Basically, the API we're going to use to interact with threads is called SP-Thread, which is based on top of pthreads, which is a very classic user-level thread management API. So you learn about threads. Everything you learn about threads apply here to this API. Isolate code execution with distinct threads, resource sharing, concurrent execution. A very efficient, light way, but you would have to deal with the overhead of managing the threads and make sure there's no concurrency problems. That's a lot of hassle. And that's why we introduce, let's talk about SP-Threads later. Basically, just a wrapper around pthread that helps you deal with all the concurrency problem. So basically, the pthread library, when you call pthread create, it basically create the threads. Join is kind of like wait. So in your main thread, if you call pthread join, you're going to basically reap the threads once they're done. And then you can also cancel a thread. This is a very high-level overview. SP-Thread is, again, a wrapper around pthread. And it provides you the ability to continue and suspend a specific thread, which is very powerful. Because, again, the problem with threads is that there's a lot of concurrency issues. We provide these functions, and they're guaranteed to not have any concurrency problems. If you want to look at the implementation of SP-Thread, it should be in the PenOS spec. At the end, you can click into it. Yeah, And the reason why suspend and continue are useful is because you would want to, in your scheduler, be able to stop and start an arbitrary process. So in this case, as you can see, we're basically measuring everything in terms of time quanta, and each block is basically one time quanta. And using the SP thread continue and suspend function, you're able to, for example, bring back a process from a stopped state, and basically be able to schedule different processes. And Connor's going to talk about the shell part.
Oh, yeah, that's fine. We have to switch it for now. Yeah, so I'm just quickly going to talk a little bit about the shell. This is like the main, I guess, part of PenOS. And I don't know what happened to our slides here. Okay, I think this is fine. So basically the main requirements for the shell are synchronous child waiting, redirection, parsing, terminal signaling, and terminal control. You guys should be like generally familiar with these concepts just from using the actual shell. Our goal is to kind of mimic that with obviously limited functionality, because it'd be a little difficult to implement everything. So yeah, the shell functions, we basically just want to have interaction with PenOS. We have two types. We have functions that run as separate processes, and then functions that run as shell subroutines. And I guess I'll talk a little bit about, can anyone tell me why maybe we might want to have processes that run separately versus that run as subroutines of the shell itself? Can anyone think of like a case where that's necessary? Okay, I guess I'll talk about, oh, yeah.
The plus on the sub the
Yeah, exactly. So basically some of the functionality needs to have access to the schedule and like the kernel and the main like logic and internal state. Otherwise it's not going to be able to execute properly. Others don't need that. So you run them separately. And so here's kind of an overview, just like he was saying about some of the processes like built-ins that might run as processes. Cat, sleep, busy, ls, touch, move, copy, remove, ps, like all those things can run as processes. And then we have some things that need to run as subroutines, such as, I guess I'll go over kind of, are there any questions about what these actually are or do? I mean, these you should probably know. But here we have some things that you might not have used. Are people familiar with NICE? Just like show of hands. Okay. So these are just for kind of changing the priority of a process. So NICE will allow us to kind of just run a process with specific priority. So we can have it as a highest priority, second highest priority, or lowest. And then NICE PID will allow us to kind of change the priority of an already running process just by putting in the PID and specifying the priority. Yeah, and this is kind of just the aside that I was talking about. Think about why it might be problematic or difficult to run certain commands from a separate process, and consider the kernel structure and the process lifecycle, because it'll kind of give you like intuition on why we're doing it this way. Hopefully that makes sense. One of the other functionalities that you guys are gonna have to implement is error handling. So we expect you to have an error header file with like a UP error, which is a user level function. And then also we want you to have global error, like no macros, and you call UP error for system errors that like arise from your specific function, like system calls. But we call the actual P error, that's the built-in for host OS system call errors because we didn't implement those. Question? Yes. So we're gonna have man, and that's just gonna be an overview of the commands that you implement. You will see that in the demo really quickly, so you get a pretty good idea of like what it is. We don't expect you to write like paragraphs and paragraphs of content for your man pages. Just a quick overview of kind of what the functions are that are available and what they do and how to use them. Are there any other questions on this slide or the previous slides that I've gone over so far? Okay. Another important concept is just kind of maintaining the abstraction. And this is, I guess, another conceptual thing that's pretty important. We don't want user land functions to be able to access kernel land. And then like the kernel should have access to C system calls, but the user should not. Can anyone quickly tell me why that might be? I think this is something you guys have talked about in lecture. Yeah, it's kind of a security thing. You don't want users being able to kind of just run whatever they want, run C system calls or your kernel system calls, which are going to be privileged. So we kind of want to keep these separate. And then once again, the shell built-ins should have access to user land because we want the user to be able to call those functions. But we do not want them to be able to just call kernel level functions because it is a security concern. And so that's kind of just an abstraction that you guys have to maintain in question. You're saying like these calls? Like the user land calls? It should just like be accessible to them. Like once again, it's something you're maintaining in your code. So it's kind of like, I guess, up to your implementation to make sure that a user can't just run the like kernel level functions, but like there's no reason why they wouldn't have access to it. So I think that might be answered in a little more detail in the spec, yeah.
Question is what?
The system functions are called within the.
Yes.
So like in code, like you can call system call functions. It's but the user itself is not called.
Yeah, so it's mostly in this chart here, I think. So like the user level code is up here at the top. It has access and can call these S functions, right? How it does it is it pound includes the header file that has these functions declared, right? But it does not pound include the file that has the kernel level functions, right? The barrier between accesses is really thin, right? It's really imaginary. It's really enforced in how you program it, right? So user level code can pound include this header file, not this one. This code, the .c code for these functions can pound include this header though. So these can be implemented by calling these. But still, if the user only pound includes the system calls and not the kernel functions, then the user level should only be able to call the system calls and not the kernel functions in their code. Does that clarify? I like to let the TAs do it, but this part is, I did not fully understand it the first semester I taught this course. This part is just hand wavy.
Another question? Yeah, no, like it's kind of just a don't, like he said, it's a very thin, it's not like proper security. Like this is not something you'd like put in production, I guess, but.
So basically, when the shell, and then when you cap the shell code would call u underscore cats. Then
Yeah.
u underscore cats call s underscore like open read and all of that, and those would then call k underscore open read. Like that's how we want our separation to go.
Like,
or would cat be lower, like it would be a system?
I think what you said is mostly correct. Let me get this. Yeah, sorry. Just to clarify, reiterate. So to also restate the question, someone asked when someone types in cat in the shell, what happens? Do we call u underscore cat? I don't think it would be called u_cat. I think there would just be a function called cat that's like in the shell code. That you would spawn a thread to run that cat function, and that cat function would call, you know, user level functions or system calls like sopen, sread. And then those functions would call somewhere the K functions. But the cat program should not be able to directly access these. This is sort of like how when we're writing pen shell ourselves, we can call the read system call. The read system call is sort of equivalent to these S functions. And in that read system call, under the hood, somewhere internal to our operating system that we do not perceive as programmers is calling special kernel functions to make it work. Why would I ever make U functions if cat can just call the S functions? I'm not wrong, right? The cat can just call the S functions, right?
Yeah.
Oh, cat is a U function. Okay, the cat is a U function. Sorry, that's my bad. But yeah, the cat itself is a U function. But in other ways it might be useful is that there might be some functions that are userland functions. Like for example, if you had to make, for example, your own strlen as a user level function, that it would be just separate from these because strlen does not need any of this shit. For example. Okay. I'm gonna stop.
Are people clear on that? I think also it'll be a little clearer once you start writing code and like reading the spec as well, hopefully.
This part is just confusing. This is probably, in my opinion, this is the most confusing part.
Yeah. Last thing I'm going to talk about really quickly is shell scripts. This is another thing that you guys need to implement. You basically just want to be able to create a script. So we hopefully know what the kind of append and write, like redirect output symbols are. So we're right here, we're writing echo line 1 to a script, and then we're appending echo line 2. We're printing that script. We're giving that script permission to run. With chmod was another thing that you guys need to implement. And then you are just, once again, running that script. And you can kind of see the output there. Yeah, you're just like writing the output of that script, then to out with the redirection, and then using cat to print it. Is what this is doing clear and like kind of the functionality that you guys need to implement here clear? Or are there any questions? Okay, one right here.
For the shell, can we use the parser code we were given for print shell?
I believe that's
That's code we didn't write, but we're given.
Yeah, that's fine. Yeah, in past semesters, that's what been allowed. Another question? Like I guess, yeah. Like you're using the file system that you guys have like worked on, so it's still part of your project, but like more or less, yes. You're just re-implementing what already exists. Yeah. Another question?
So like, let's say you created a file. Is that like stored that, or is it like stored outside? Container that you're running. It's like this variation.
Yeah, it would be within PenFat. So like that's kind of the point. Like we want you to kind of recreate the file system and then also the shell. So it would be within PenFat. Like obviously something. So like it's not just going to appear in the like file system locally and you run it that way. Does that answer your question? Okay. Another one. Yeah, more or less, you're like allocating memory. Like, correct me if I'm wrong, Akash, but you're more or less like mapping memory and then creating your own file system to like organize that memory. And then that's how you're like dealing with your files and all that. It shouldn't be. Another question there? Okay. No, I don't think you need to worry about that. Yeah, I'm pretty sure yeah, it's within memory. Like, I believe, what do we use, mmap? Yeah, so it's like just mapped memory. Like, that's kind of what I was just saying. Like, you're just mapping like a portion of working memory. And then that's your file system. So you're creating like the structure of the file system within that memory that you just like kind of allocated. And like that's where you're implementing like all the operations like the penfat and stuff like that. Did that make sense? Okay. Any other questions? Or, oh, one over there. Yeah, like in a perfect world, that all gets deallocated. I think zero memory leaks is extra credit. But it is, right? Okay, it is, but like, please, like,
You have memory errors? So that will affect.
yeah, because yeah, if you have like actual, sorry.
Any invalid read writes, fix those. Still debug with background.
Over there. Like that's I would not advise that just because like you are gonna run into errors and you're like, why is this not working? Like, why is this output not as expected? And it probably traces back to, like a memory leak somewhere or something that you didn't free. Or like, if you just don't deallocate like all of the, like, surely we don't get full point. You just don't deallocate like any of the memory.
You look at your code when you do the PenOS step. So, you know.
Maybe we'll change it. Maybe we'll change it this semester. No, no memory leak is not extra credit. Anything else, or are people kind of clear on this section? So we can go to like the demo and stuff, because you guys are gonna want to see that.
5 minutes left.
Oh wow. See how like I don't even know.
Do part of it. Do part of it.
You sound like me.
Just finish early.
That's true. I didn't mean to take too long.
If we just speak. No. What is that? What's the top? Travis.
What's this for? It's all, don't worry.
I think it's
all
for the
on
mic.
Zoom. That's
Wait,
fine.
Travis, he doesn't have a USB.
Yeah, there's dongles and stuff. That's why it's all positive. To make sure that okay. Hold on. We have this. Fuck, where's the floating meeting controls? Oh, here, down here. Oh, down here, down here. Okay. Okay, sure. And then, well, the camera should be going through this. Huh. Don't worry about it. Don't worry. Let's go. Okay.
Okay, I'll make this quick. I'm gonna start with the like demoing the fat part of it. So the file allocation, this is like more the standalone fat. So what you would need for, I think, milestone 1 to have done. So you're gonna have a standalone fat, so what you're gonna have to do, like when you after you compile and make everything, you're gonna have bin, it's gonna be in your bin folder, or you can change the output to wherever you want it to be, and it'll be pen fat. And then now you like are in your like little pen fat thing. So here's where you want to make your file system. You do mkfs. You need help with that? I can just hold it. Okay, right. Oh, high tech. Okay, anyways, mkfs, and then like it'll be like your name, the name of your file system is like minfs, for example, and you do like 10, which is what the block size and the whatever the thing is called. Huh? Yeah, number of blocks in the fat size. So this is like those are the parameters you need to enter, and then now you made your like file system. Like that's your entire file system, and you can see it here. It's made in your like this is your host system before you ran to like your little like penfat system. So in your host system, you see the minfs, and then if you do a hex dump, because the file system would be hexed. This is the output you're gonna see. So this is the like where you enter 10. This is like parameters you specify for how large the file system is. And then there's currently nothing in it except for some like directory information, but because it's empty. And then in standalone fat, you had to manually mount the file system. When you get to PenOS, like the actual thing that's not standalone, it should automatically mount it. But you would need to do minfs to actually mount the file system, and you'll see a little slash here to know that it's mounted. And then you can also unmount, just you mount. Oh. Okay. That's all everyone. Okay, 10.5 is code results. You can also mkfs with different parameters, like you can make a full one, like maxfs, you'll probably need this later. This is a much bigger one. Instead of like 1 block, it's 32. And if you do a hex dump on maxfs, oh my god. What am I doing today, guys? I'm not this today. Okay, minfs is 10, and then maxfs is 34. And then this is back in the right one is your root, like this is your host system. So like your Mac, your Windows, or your Docker container. And then this one you see like this is a much bigger, it goes down to much like the letter number on the side tells you like what address number it is. And you tell it's much like larger, it goes down to like 2060 instead of like 170 blocks. Okay, so a couple of commands you might want to run in here. What you can do is you need to be able to copy things. Oh shit, sorry, if I ask you to unmute though, you don't have to press the wrong button. So for example, if you make a file on your host file called like hello file or something, and then you put hello in here. And then you save that. So that's in your like host file now. So you have that. It's so annoying. Jeez. I'm trying to do this fast. Okay, so now you have your hello file, which just says hello in it. And then when you mount your manifest, you can copy it. So you do cp -h is the flag that you have for if you want to copy from the host system, like your host like operating system instead of the another file inside your penfat. So you do that and then hello file, and you do like file 1 f1. Now you ls, you have your f1 here, and now if you do a hex dump of manifest the file system you made, you should see hello pop up on the bottom. That's the and then something along here will link it to this address block. So notice that like file f1 here is linked to this address here, which is where it starts. You also need to be able to handle remove functions, so you can also remove f1, and that should be gone. If it's not gone, you have some issues there. If we put it back, it again. You should always also be able to rename certain functions. So yeah, rename you can just do as like a move, like rm or mv, which is like the move function, like you move to different like location. But if you just change the name of it when you move it, like everything in there will stay the same because you just copied it basically. So if you do mv f1 5 or something, so now your f1 is gone and your f5 is renamed. And if you do hex dump of manifest back in your root directory, now it's an f5 and it still points to the same one. And then you also need to be able to handle unmount. So if you see you have your f5 here, if you unmount, what is wrong with unmount?
You said you mount.
Oh my god, guys. Cannot type today. Jesus. Okay, so now your file system is not mounted. So you shouldn't be able to run any other commands like if you do ls. Now like a bunch of jumbled stuff come out. So now if you run penfat again and then you mount minfs and you do ls, like all the information should still be there. So every time you unmount, you kill the program, everything should be saved. And it shouldn't be like a local copy or anything. I think that's all the important things that we need to see here. I don't think we have time. I don't know if we have time to do a shell demo if you just want to demo anything. But we have 1 minute. Okay, I'm gonna call it a day.
All right, so it is, let me take the mic. It's 1:29, so we didn't get a chance to do the shell and the kernel demo. But it's still useful, so we're probably going to put a recording of it on the website for y'all to look at. Highly recommend to do that. What Zihao just demonstrated here is sort of for what you're going to do for milestone 1, not milestone 0. Milestone 0 is milestone 1. Milestone 1 for the back. And it didn't look like much from his end, but there's a lot that goes into it. With milestone 1 is about 60%-ish. Hopefully it helps with something.
Oh, I cannot spell today, Jesus. You mount.
The repo is going to be. A lot of things are going to, the auto grader for making repos will be posted soon. We'll also make the rest of the pairs, and the pairs will be posted after midnight tonight or tomorrow morning, along with the TA that you are assigned. If you have any questions, we're all up here still. So here to answer questions. Best of luck. And yeah.